recording. Now I'm actually recording right now. Okay, thank you very much for reminding me. So this is the so-called IEEE Microwave Theory and Technology Society Distinguished Microwave Instructor Program. And this particular activity is initiated under the Education Committee. And, I organize this event along with my colleagues like Professor Cherry Cher and other colleagues around the world. So this is, excuse me, so I thought I would suggest somebody can mute yourself unless I think I hear some noise in the background. So this is our third DMI workshop. The first one was in last November. That was for the region 10. And the second one was in last May. And just the past May, that was for region 8. And this is for North and South America. Now, the purpose of this program is to excite the students into microwave engineering. And there are so many interesting things in microwave engineering, particularly due to the wireless technology at this moment. And we would like students to know more about this field, and before they decide to pursue something else, like machine learning, artificial intelligence, they are cool, but we have cool stuff as well. And today we have three distinguished researchers and educators in this field. And we have Professor Rhonda Franklin from University of Minnesota. We also have Professor Zhenshan Lin. He used to work for University of Florida. Currently, he's a program manager at the National Science Foundation. We also have Professor Andy Zhu from Europe, actually. He's a faculty member in Ireland. So this is the layout of some information about this program. And so the format of today's program is like that. So each DMI speaker will present for 20 minutes, all right? Then at the end of the three presentations, so we will open a Q&A session. Now, I would ask all the attendees, first of all, mute yourself. Secondly is to type the questions in the chat, okay? So then we will address your questions. And we will expect to, complete this meeting around 1:40 or 1:45. If time is needed, we can extend a little bit. And also, for those of you, I know that we have a couple of faculty members who actually, they invite the students to a classroom and do a group meeting, in-person group meeting. I would ask those faculty members to take a photo of the students in the classroom and record the number of attendees. We would like to have a nice report after this event, okay? And send it to, you can send it to Professor Yang and or myself, either way, that would be fine. Okay, so without further ado, before I actually move on to the presentation, let me just show one thing real quick. Is that this is our society's website, IEEE MTT, MTT.org website, and you can find a lot of good information there. I'm currently also hosting the monthly webinar for the society. So you actually can see the announcement of the webinar, including today's DMI webinar there. Okay, and feel free to log in and to register, and you will learn a lot of great stuff. All right. So without further ado, I'm gonna actually move to Professor Rhonda Franklin, and let me do a quick introduction. Professor Franklin received her bachelor degree from Texas A&M University and a PhD degree from University of Michigan in electrical engineering. And she is currently a professor in ECE department at the University of Minnesota. And her research investigates design of circuits, antennas, integration and packaging techniques, and the characterization of electronic materials and magnetic nanomaterials for communication, biomedical, and nanomedicine applications. So Rhonda, please, you can share your screen right now.
Thank you for that introduction. So let me share. It looks like it's already there. So let's see. Oh, yes, it's already here. Okay. So can everyone hear me okay? I don't know how you say thumbs up or whatever, but if one person says yes, I'm good, I think.
Yeah, you are good.
All
Yes.
right, so good morning. Thank you so much for making time to come and listen to this presentation. And thank you, Sean, for that introduction. I would like to talk to you today about interconnect technology, wired and wireless, and that to help you understand the importance of interconnect technology as being the nervous system for high-speed applications. Oh, it's not moving forward. Hold on. Maybe I did not share. I thought I shared the screen. Do you see the screen? I'm not able to move the screen. You do. Let me try it again. Sean, stop sharing screen. We'll stop. Okay. I think it's not, I think it was not seeing my screen. I think it was an artifact of the previous screen. So here, I think this is my screen. So I'd like to start off by us paying attention to the fact that any system, any complex system, has a number of features associated with the way that it operates. And most of the time we think about in the human body, we think about major organs like the brain, the heart, the lungs, and everything else. And of course, we know that there's a nervous system there that allows signals to move from the brain to the different parts of the body and back and forth. But a lot of times the nervous system is actually is sort of a unappreciated part of your body until you have pain. And then you worry. So what I'd like us to think about is, let's think about systems of the past and where we're going today. And then I'd like to kind of bring us into
Imagine doing your lab report on time.
I'm sorry, I can hear someone speaking.
Excuse me.
I can hear someone speaking.
Yeah. So could you please let me actually yeah. Could you please mute yourself? I think I hear David Brown. Could you please mute yourself? Anybody, could you please mute yourself? Yeah.
So in the early 1980s, which is where a number of my undergraduate students would have been born, we had devices that were really individual pieces. And you could see things like computers and cameras and printers and pagers and telephones, but they were all individual components and they all performed a single individual function. Between, fast forward 2 decades into around 2000, all of a sudden we started looking at integrated devices, which could be where integration really meant at a minimum combining two functions. So with computers, the addition of communications was an integrated system. With phones, the inclusion of a way to take pictures was an integrated system. Of course, today we expect many of our phones to be smartphones, and those are highly integrated. And after we figured out how to integrate cameras and telephone for communications and computing for internet access into single devices, it really motivated and stimulated thoughts around the concepts of Internet of Things. Well, what if we could communicate to all kinds of things, not just each other, and if we could control those things? The Internet of Things then lays the foundation for us to think about highly integrated system applications such as autonomous vehicles, smart systems, smart connected cities, and so forth. And these things require us to then advance our communication systems technologies, which is what puts us today to begin thinking about things like 5G. So that's the basis or the premise for what I would like to talk about today. Now, in doing so, it turns out that when you think about interconnects, you may say, well, what are interconnects and, why do we need them? If everything is going to be wireless, who cares? Well, it turns out that interconnects are important because they do two jobs. They transmit power and they send signals. And so on the left, you'll know that many people, including myself, are very frustrated when we have all these cables that we need just to turn things on. You can see I've given an illustration of a power cable that's used for underwater applications. And then on the right, you can see that when I talk about an interconnect being responsible for propagating a signal, it has to send the signal itself, which is an AC signal, generally speaking. And then it also is responsible for propagating different modulations that may be imposed on top of that signal. So the interconnect is the nervous system of all of our electronic communications. So if we go back and take a step back to yesterday, prior to 2000, maybe even 1990, almost everything needed a cable. We needed a cable for telephones on the left, which then became cordless phones, which happened when I was a graduate student. And a cordless phone wasn't a wireless phone necessarily, because the signal from the telephone company went into a base, and that base signal was being sent wirelessly to a handset. So it was considered a cordless phone. We had televisions that required power, but they also had antennas, so there were cables for that. Today we have TVs that have remote controls, and they're much smaller and they have less connectivity requirements, especially if there's a wireless interface to them. And then, of course, there's the computer, which generally speaking had power, but it didn't have other features. And now you can see that we have not only computers that can communicate wirelessly, we have laptops and all different types of versions of computing that integrate laptops, integrate video cameras, integrate all kinds of things that would have been done separately with their own appropriate interconnects. So what's interesting is that we are moving forward in certain applications to having these things done wirelessly. And shortly, you're going to hear about that with my colleague, Professor Lin, when he talks about wireless charging and the power of invisible waves. So I'm looking forward to hearing about that myself. But what I'd like you to see is that today we have hybrid systems that integrate both wired and wireless systems. So for example, this picture on the left is actually all of the colors that you see are wires or connections to different computers that happen at one of the cloud stations for Google. And if you look on the right, you'll see that they're communication networks, and these white things and gray things that are round and circular, which are various antennas, they have physical wires connecting to them that actually will take signals or send signals to do processing that go to physical hardware. So those things are really, really big and bulky. They require a lot of power to drive them. But there are aspects of our communication system, particularly where you have devices that connect, that are really starting to need more bandwidth. And that is moving us toward 5G. And notice with 5G, the system that is very, very large on the right for one antenna connecting to its appropriate hardware is now miniaturized and into this single device. And this is going to be the subject of the conversation of Professor Zhu a little bit later. So in communications, we have the backbone, we have devices, and both of them require some type of cabling. In the backbone, it turns out that a lot of the backbone evolved from the first generation based on data rates of 2.4 kilobits per second to where we are today, which is looking at 5G, which is running at about 10 gigabits per second. And what that really means is that we have to have wires or some type of transmission mechanism that can handle those really, really high speeds and preserve the modulation that I showed you earlier, that is the information that is riding on those waves. So if we think about what's happening with respect to 5G, you can see here that we have a lot of technologies that are spanning a large range of frequencies, things that are operating down in the 300 megahertz, which are more device related, and then moving toward in the direction of 30 gigahertz, and in some specific applications higher. But all of them are requiring us to rethink how we build a transmitter transceiver system, and those signals that are moving in a circuit based on a chip or between circuits based on an antenna require us to really think about what the interconnect requirements are. So let's take a step back and think about wired interconnects, for example. I believe that you can expect to continue to see physical wires, particularly for large scale systems and high power applications, because we have to have a way to move energy safely among various things. And you can see that on the left with AC signal distribution. We have computing, for example, with quantum computing. We have rigid wires that we can use to transmit signals. We even use cables to do sensing for earthquake detection underwater. And so these things will be here to stay, but they will have much more niche roles that they will play in our overall system. However, Because of the number of devices that we have coming on board to utilize in the communication system, wired interconnects for small scale and small power or low power will require us to think about novel chip scale technologies. And these chip scale technologies fall in about three categories. There's wafer scale integration, chip scale integration, and then I'll talk to you a little bit in the next slide about system integration. And when we think about wafer scale integration, we're saying let's take some base material that we would normally build a circuit on, and we've got to figure out how do we do different layers, but we make interconnects on the plane, but how do we also create connections between the planes, which we call vias. And in this picture on the left, you'll see that the word via is here, which is basically connecting level 1 to level 2. On the right, you can see that we also can think about chip scale integration. So given a computer chip, how do I actually put those together in a planar form and make the proper connections there? And in that case, we have a chip that has its own interconnect technology combined with other chips based on their interconnect technology and their particular technology for implementation. And we have to find common ground or common ways to connect or send signals between those. So you'll see wires here that are the result of this. Someone wants to annotate the slide. I'm not sure what that's about, but I'm going to decline you at the moment if you don't mind, Warren. And then what I'd like to also talk about is the role that novel materials are going to play in the future for developing advanced interconnect technologies that are some time away from utilization. In my group, for example, we've been dealing with looking at nanowires and their co-integration with silicon, because silicon is such an important technology for a lot of our communications. And with nanowire technologies, you can imagine that we have really small wires that are on the order of nanometers, and we're using that to actually create vias that have 1 million wires, thousands of wires in parallel to try to control resistance. And if you look on the bottom, you'll see that we've been able to observe that our losses associated with those can be quite small. We have another colleague who's been doing that similar kind of work in a different substrate, in aluminum AAO, anodized aluminum oxide, and they also see really good results by taking advantage of advanced fabrication methods to achieve improved performance. So I'd like to switch over a little bit and just talk a little bit about system in a package. That's the third one. You'll see here that system in a package makes the assumption that I've got different functions incorporated. And if you look at this picture on the right, you'll see that there are a variety of interconnects. There's a physical interconnect, which is based on a wire bond. That's these curly wires that are connecting one chip to another chip based on this to connect to this substrate. You can see printed lines on the substrate, which are also different types of interconnects. And you can also see that just at the interface between the rectangular blocks of different components, that the physical transmission line is very, very short, but there's an interconnection that does occur at that point, which needs to be thought about. And the picture in the back with the gold, you can see that there are bumps that are used to attach this particular device here. So in a system on a package, the types of interconnects that are involved can be quite complicated and quite diverse. And if you look at the bottom, you'll see additional balls, which allows this whole system to then be connected to a different system for integration. The transitions between these various lines, as well as the lines themselves, are subject of a lot of research, but they also are very important because they can really hinder the overall expected performance from a device. I'd like to move briefly to talking about wireless interconnects or antennas, and those can come in a variety of forms. I've just kind of pulled some random ones here, but we can have chip scale antennas, as shown at the top. You can have chip antennas in a package where you can see that the antennas are actually integrated into a package component for these two. Another technology that has been developed more recently over the last 2 decades is substrate integrated waveguides. These are really nice because they allow you to integrate waveguide technology into a planar technology in order to get some of the benefits that waveguides offer, particularly around low loss and the ability to offer more power handling capability. And on the bottom, you'll see that there's also the ability to think about integrating antennas with lenses in order to get more focused beams. And these focused beams can also be used in applications like vertical free space interconnects, which allow you to send beams into this plane, and then those beams can be picked up and used to feed some other chip. So, how are these advanced interconnects developed? Well, they're developed using two basic ideas. First, there's the design process, and then there's the test and measurement. So with design, we usually use a variety of different microwave design tools. But there are a number of vendors. In my classes, I tend to use Keysight, but we also have ANSYS for some of our more complex things. We really care a lot and need to know about materials characterization because, as you can see, there are a lot of different materials being utilized, so you need to be able to know the performance before you build. And then we need to understand what the specific design requirements are for the interconnects that we're building and what are the isolation requirements, in particular for things that are in really small spaces. Afterwards, you just have to evaluate your test and measurement method. If it's wired, you can use a vector network analyzer. Sometimes you can get away with high-speed oscilloscopes. And if there's a digital application, you might want to look at bit error rates for the modulated signals. And then for wireless ones, again, you would want to characterize your antennas initially with the VNA, take some antenna measurements, and then think about for the application over the air testing. So for my last slide, I just would like to also get you to think about, if you're interested in this, how do you explore this more? Well, the first thing you can do is take some classes at your university or uh, at some of the workshops on passive RF, active, and antenna design. You can join the MTT Society. I have a link here for a section of that which has a component associated with packaging, which is shown here in the lower right. But sometimes some of the campuses also have a MTT-S student chapter that you can join to learn more about this. You can also read journals. The Microwave Magazine is great. In fact, I think this past cycle, there's a really nice set of articles on packaging and interconnects that was just printed this year for 2022. But there's also the transactions on MTT and the microwave wireless component letters. And lastly, I'd like to just also let you know that there are also opportunities for students to participate in the student design competitions. And the area that I work in, which is the technical committee 16, we offer design competitions along with many of the other areas in the society for students to just get a chance to learn and apply what they know in that setting. So I'll stop there. Thank you.
Thank you, Rhonda. Very nice presentation. Many beautiful pictures, and I think very exciting technology. And I think these are the enabling technology behind the many useful application, including your cell phone, radar, and sensor, all kind of stuff like that. So thank you so much. And
Thank you.
so I will encourage all the attendees to think about the questions and type in the chat box. And for those students who are in a classroom, just provide your question to the moderator in the classroom and let the moderator enter inside the chat box. And we'll get to the Q&A session at the very end. Also, just want to remind everybody is that this particular webinar is recorded and we will post this recorded video to the MTT Society website, and it will be free to everyone. So I encourage you to distribute it. You can watch it again and distribute it to your friends and colleagues, okay? And let me introduce our second speaker, Professor Jianshan Lin. And Jianshan, you can share your screen while I'm reading your bio. So Professor Lin received his PhD degree in electrical engineering from UCLA. He is currently a program director at U.S. National Science Foundation and a professor emeritus of University of Florida. In his early career, prior to joining University of Florida, he worked in Bell Labs, and it's a spin-off called Agere Systems. Throughout his career in industry, academia, and government, he worked on several wireless technologies for communications, sensing, and power, and he is now managing funding programs covering those topics. Jianshan. I think you are muted, Jinshen. Jinshen, I think you are muted. Could you please unmute yourself? Let me send the unmute request, but I think you should be unmuted. Jen, I think we are not hearing.
Sorry, when I share the screen, I lost all the control.
Oh, okay. So, all right. Okay, you're good now.
Let me redo it.
Yeah, redo it. Yeah, go ahead.
Okay, hold on a second. I have many screens, desktops. Okay, I hope this time it works. No?
Yeah, we saw. Yeah, we see.
No, I shared the wrong one. Sorry.
Oh, wrong one. Okay.
It should be this one.
Okay, that's good. Wireless charging.
Yeah, this should be correct. Okay. Thank you very much, Professor Gang, for your introduction, and it's a pleasure, and thanks for the opportunity to share my perspective on this interesting topic with you for wireless charging, the power of invisible wave. And then Professor Franklin mentioned about the interconnect, both wire and wireless interconnects, and also mentioned about power cable. And the concept of wire charging actually is trying to cut the last wire interconnect, the power cable. So you notice that in the title here, I said the power invisible wave. I didn't say microwave, I didn't say RF wave, I didn't say electromagnetic wave, because there's a possibility using acoustic wave, other type of a wave to actually transmit the wireless energy. And that's why I just simply use wave. Although my presentation following this will basically focus on using electromagnetic wave. So that Professor Gao introduced my background. So I just want to quickly go over that, my journey from a student to a retired professor. I got my bachelor degree in Taiwan, National Chiao Tung University, not in electrical engineering, but in electrophysics. So which is kind of argument saying that it's a 50% electronics or 50% physics. Okay. And later on, I came to the United States, UCLA, for my graduate study. And I chose the electromagnetics in electrical engineering as my major. So that's where I ended up doing my research and teaching for my career. So after I graduated in 1994, I got a chance, opportunity, the job offer from Bell Labs, which is a very famous research facility in New Jersey, because that was the time for wireless communication started to rapidly grow from 2G to 3G, eventually up to the 5G today. So they hired me to work on the early development of wireless communication circuit systems, and in particular the early development of 3G cell phone chipsets. And I also work on some other high-speed interconnect the devices. And the last 2 years I stayed in New Jersey, I actually ended up joining a spin-off company from Bell Labs called IEEE System, basically the microelectronic arm of the Bell Lab or the Lucent technology at that time, and focus on actually not the wireless, but actually optical high-speed communication, 10G and 40G optical communication. 2003, I decided to actually pursue an academic career. I went to University of Florida, first as associate professor and then become a professor, doing research in communication, sensing, and power, and mainly for using wireless technologies. And I recently retired from the University of Florida. I become a professor emeritus and to join the National Science Foundation as a full-time program director. Because of that, I had to leave the university. And then throughout my career, I've been focusing on wireless technologies, whether it's communication or for sensing or for power, even though I sometimes still work on the non-wireless, which is wired, the technology. And you can see that basically I spent my career first in industry and academia, and now I ended up in government. So in terms of wire charging, you might be wondering that you have electrical toothbrush that actually, you can say that it's actually using wire charging, right? And that has been there for quite a long time. So what's new on this topic, wire charging? So I would like to ask you to look at the picture here. The wire charging for electrical toothbrush actually very simple. Essentially, just breaking the transformer, cut in half. One half in an electrical toothbrush, the other half in a charging cradle. And there's no degree of freedom in placement. Okay, you can say it's wire charging, but it's quite limited. So, so what's the new wire charging about? So let me use this video to actually illustrate that. See if I can enable this. Okay. So I'm using the light bulb as an example, not using cell phone. So you can clearly see the power being transmitted wirelessly to the light bulb so it's light. You don't get a power until you get very close to the so-called wire charging pad, the device, the black pad device there. And once you are on it, within the areas of the pad, you actually can receive power. And the pad actually can charge multiple devices simultaneously. And then you have a large degree of freedom in terms of movement, of placement. So let me quickly go over that. And then as soon as you leave it above the pad, you lose the power, so you don't see the light. And that's the idea of new wire charging. It gives you flexibility, it gives you freedom in movement, the alignment, and potentially you can extend the distance. Okay. So in fact, the wire charging indeed is not a new concept. More than 100 years ago, the Tesla actually proposed concept of wired power, the idea, and he actually did his first experiment in 1899, tried to use 150 kilohertz to do the power transmission without wire. So it didn't take it took a long time for actually the concept to start become materialized. And more than 50 years later, 1958, the first period of microwave wireless power transmission R&D began in the United States. Okay, and the reason why it took so long because we need a solid-state technologies, semiconductor technology, mature enough so that some key devices on the receiving end can be made very small, lightweight. So when it started, actually, in the United States, Raytheon, Air Force, NASA actually invested into this wireless power research. And that's a particular important researcher in the history called Dr. Brown in Raytheon. He demonstrated the first microwave wireless power transmission system. He used microwave frequency for a longer distance. So in 1963, he demonstrated that. And in 1975, he actually demonstrated 54% DC to CC efficiency. And with the 496 watt, nearly 500 watt achieved at a 170 centimeter transmission distance. The same year, he also demonstrated that 1 mile distance away, you can send 30 kilowatt DC to receive by receiving end. And here shown the picture, a famous experiment. In 1977, probably because of the energy crisis, all of a sudden interest started to show up that, oh, how about we can collect the solar energy above atmosphere and then convert to microwave and beam it down to Earth, so that if the attenuation through atmosphere will be smaller. Okay, that's called solar power satellite concept. So NASA DOE invested in this research development, and that's called the second period of microwave R&D in USA. 1995, NASA also come up with another program called Solar Space Solar Power SSP program. However, nowadays we don't have a commercial system that actually can do this, to collect the solar energy from the space and then beam it down to Earth. And then there's been a lot of experiment going on, but still for it to take off, I mean, it's not happening yet. However, on the other hand, there's a wire charging actually becomes successful in different areas in terms of charging mobile devices. Why is that? That's basically because of rapid growth of the wireless devices. You have so many cell phone wireless devices nowadays. So because of economy of scale, like a large number of consumer electronic devices, and that we have a wireless communication booming, so many smartphone wearables, and that's why the wireless charging become a very popular nowadays. And another reason also because the industry or the people, engineer pick the correct frequency band to do this. Pick a lower frequency band. They pick initially less than megahertz, low frequency. So when you come to a low frequency, power electronics will have a high efficiency, and you go to higher frequency, efficiency is going to drop. That's the reality. So because its efficiency is up, so make it more realistic to do wireless charging, and also the safety, because we use lower frequency, use predominantly magnetic field, magnetic energy. So near field magnetic energy coupling, and then in this case, at low frequency magnetic field, the human RF exposure safety we can easily certify, which I'll show some slides later to explain this. So for efficiency, when we talk about efficiency, usually we'll talk about the overall system efficiency, all the way from the DC you put into a system to wireless power transmission to receiver end, and then convert into back to DC again. So that's a conversion from DC to AC, transmitter side, and then send it into the antenna or the coupling coil, and then through the space, and then received by the receiving end, and then convert the AC signal into the DC again. So there would be a lot of efficiency loss through the process. The total system efficiency, you have to multiply all of them together. And any one of them has a low efficiency, going to drop the basically drag everything down. You have to get the overall high system efficiency, you really have to achieve very high efficiency in all different stages. So we got a high the efficiency in terms of the source converter efficiency and receiver converter efficiency at low frequency because power electronics. And for the transmission efficiency, whether you use antenna or coil coupling, it turned out that for the near field range, using the coil, the couple together, actually you can achieve higher efficiency than using antenna transmission. So, and that's why overall in this case, using low frequency magnetic field inductive coupling, it get the efficiency up. And that's what the current wireless technology standards using right now. So in terms of safety, I'm using this IEEE, the guideline to explain that. So this is basically taken from the data from this IEEE International Safety Guideline for RF exposure. I took the data and make the plot. The data basically look at the either electric field or magnetic field at low frequency, and look at power density at high frequency. So if it's the electromagnetic field in far field, E field, H field are related, and then you can calculate about power density. So we can have correlation from left-hand side y-axis to right-hand side y-axis. So assuming it's a far field condition. So in this case, you can see that if you lower frequency equivalently, you actually can allow the more power to be transmitted or collected at a low frequency compared to higher frequency. And that's the lowest, the most stringent requirement actually happen between 30 megahertz to like 300 megahertz, this frequency range. So the data basically calculated from the specific absorption rate of how much temperature increase for the power received. So somehow in this region, the human body easier to absorb the electromagnetic energy. In a lower frequency, the electromagnetic field probably just see your body as a more transparent material and then passing through. Okay. So that tells you that working at a lower frequency, you can send higher electric field, magnetic field, equivalent to higher power density into the receiver side. So compare the electric field and magnetic field, you find that actually magnetic field allow the higher equivalent power density to be transmitted. And that's why eventually we use a magnetic field to do that. Also, human body is safer under the strong magnetic field compared to electric field, because human body is basically the dielectric material, not the magnetic material. the only place you need to worry about that mainly is your brain, because your brain has an electrical current. So if you moving your brain, your head through the even static magnetic field, you're going to induce a current. It's going to cause you to have a dizzy reaction. For example, if you move too fast in an MRI scanning machine, then there will be a dangerous situation. That's why when they send you into an MRI magnetic ball, they have to do it very slowly because strong magnetic field. Okay, so my group got involved in wireless power research in about 2005 and really took off. And in 2006, one of my students in my antenna class, his name is Ryan Zhang, he actually came to me, asked for help, because he founded a company initially called not a white power, power pad, and then later on changed to white power, and he has some technical issues and asked for help. So I put my graduate student together to work with him. We collaborated, eventually come up with 2 important patents, and the company later on acquired by the Qualcomm, and that's why Qualcomm later got the white power logo with their product. And the concept basically just what I demonstrated using a video previously, that charging pad devices that you can put a cell phone, smartphone, or other wireless devices on top of it to receive power, and you don't need to have a very strict alignment. You have freedom on this 2D surface. It basically uses a low frequency magnetic field to do a charging, about 100 kilohertz, between 100 kilohertz and 200 kilohertz. So this is basically a 2D wire charging pad. And you can consider that the electrical toothbrush actually is 0 degree, because no degree of freedom in terms of placement. We also demonstrated wireless laptop charging, and I guess it's found as the first report wireless laptop charging back in 2010. Basically, we took the Dell laptop and then removed the battery, put in a wireless power receiver, so that we can make sure that the power the laptop is using not from battery but from the wireless power. The total power required for this operation is 32 watts. So we're able to do 32 watts power delivered to this laptop. And this is a wire charging station. It also gets a load detection circuitry and algorithm here to make sure that when you place a invalid object like a metal plate or something else, something metal, that it won't charge. Only when you have a valid load, it will start charging. So nowadays, as of now, 2022, we have a lot of wireless power, wire charging products you can buy. And then many of them actually is unbelievable, inexpensive. I would say that I never would imagine that the cost would become so low. And then make it very affordable for everyone to buy it and to charge your wireless devices, whether it's a smartphone or whether it's your AirPod or other devices. And the most popular standard is the Qi standard right now, but there's also other standards coming up using slightly different technologies, but still using magnetic field. But the potential can give you a more degree of better alignment freedom, because Qi standards still usually require quite a very precise alignment. So not just for wireless devices, a smartphone, wearables, but the wireless power can potentially also help the electric vehicles to charge electric vehicles batteries. So a long time ago, there's already a concept called online electric vehicle, where you have a bus, just follow a specific route, and then where the wire charging cord is embedded below, so that just like the electric, the train, then you can receive a power wirelessly. So several companies actually trying to develop this product. So moving into the other the possibilities that all those previous slides have shown is basically 2-dimensional pad for charging. How about we have a box, a 3D wire charging box? Then you can charge multiple devices, just throw it in and then make it flexible to charging. So my group also did that a few years ago, actually several years ago already, to charging multiple devices in a 3D wire charging box, and we designed a coil surrounding the box and to make sure that the magnetic field inside is uniform to be able to charge multiple devices at the same time. And another project we did in the past is the wire charging of smart garments, okay, whether it's on a hanger or inside a drawer. So inside drawer is just like also a 3D box. You can just fold your smart garment with a sensor and then battery, chargeable battery there, and then put it in and then start charging. And not just one T-shirt, but two T-shirt possible. Okay, so we did research together, collaborate together with analog device to demonstrate that. So some other, okay, this hasn't happened yet, but I'm just thinking loud that could it be possible that we can do something like using microwave oven. So all previous wire charging been using low frequency RF and predominant magnetic field. But if you go to higher frequency, the wavelength is shorter, you actually can achieve more precision delivery of power into particular location. And then for that, let's say get into the microwave frequency range. Then can we turn the micro oven into a wire charging box? Okay. Why micro oven? Because micro oven has a very large power, like kilowatt level. But we are safe outside the micro oven because it has a shielding. It prevents the power from leak to the outside. So we are safe, even though inside is 1 kilowatt. Now to do wire charging using microwave, we probably don't need a 1 kilowatt, especially for those low power devices. And then we can tune it down. But still, in terms of human safety, that's a very stringent requirement. And then we still need to have a shielding box if you want to crank out the power to charge a device faster, like the electric vehicles supercharging station to charge much faster rate. Okay, so that opened up the a research possibility that because how do we make this happen? And if this can happen, then basically you can utilize a few technology sort of being used in the wireless communication nowadays, including massive MIMO, using multiple antenna, and can you do a 3D beamforming to actually direct the energy into a particular spot? And can you combine with the TDMA, FDMA, which is long being used since the second generation cell phone, to actually share, whether in the time domain or frequency domain, to deliver power to multiple devices. Okay, and certainly there will be challenge that if you don't care of using the device, you put it in to charge, that's fine. But if you also want to have the smartphone to receive a phone call simultaneously, the wireless communication frequency has to go through the shielding inside. So that means you need a frequency selective shielding. Possibly can use some kind of advanced microwave technology to do that. So in terms of the 3D charging, let's go down to a larger scale, room scale. So researchers, industry companies also invest into this. They're thinking that can you have a wireless technology that can charge devices in the room, okay, using say microwave frequency 2.4 gigahertz without causing any safety issue to your human body. So here comes the technology, basically using retro-directive array, that your receiver first send out a beacon, okay, through the multipass and to the transmitter array, receive it, and then using retro-directive array reverse technology, and then send a signal back to the receiver, right? And that's idea. So your human body is not in the path of those multipass electromagnetic wave beam. Similarly, some researchers also trying to use the low frequency magnetic field to do this in a large room scale wire charging. So this is a paper published in Nature Electronics last year, and basically using the 1.2 megahertz magnetic field. And the researcher construct the prototype room that using two different modes to actually ensure the magnetic field is uniform, also direction can be scrambled to charge the devices, whether it's a lamp, a fan, a phone inside the room. And while in the simultaneously make sure that human safety, RF safety exposure, the center is met. And they demonstrate 100 watt maximum input power, basically because limited by safety. So lastly, I want to move into the potentially disruptive concept into the micro scale. And the concept can potentially change the future product design. The idea is that into the semiconductor IC chip, can we have wireless power IC chip and make it chip scale wireless power transfer, so that you not only you can have a wireless interconnect between chip for communication, but you also don't need to have a interconnect, physical interconnect to get a power. So completely wireless. So you can imagine that for those you probably have seen the semiconductor chip fabrication and packaging testing. In this case, your packaging would be much easier. And then also testing will be much easier because you don't really need to have the probe card to probe each IC chip. You can just send it through the conveyor belt and then let it be done wirelessly and provide a power, test the chip, let it go. Provide a power, test the chip, let it go in fast throughput. So this new concept of wireless power chip could potentially revolutionize the semiconductor industry. I call it wireless Internet of Chips, wireless IOC. And you might think that, okay, some of chip probably is high power and not doable at this moment, but some of the chip actually get into a low power, especially in the future. We talk about low power IC chip, even including low power CPU, then this could be possible in the future. So with that, okay, they come out with a new product design concept enabled by this wireless power IC. So not only the testing and packaging, but the system integration assembly will also be different. So imagine that you don't need to have any wire interconnect to the chip. Everything can be wireless. Then you have a PCB to mount, printed circuit board to mount those chips. You don't need to solder it. Okay, you just place it on the PCB that had the wireless power bus built in. Then it will receive power and it will start doing what it's supposed to do, communicate wirelessly. And in terms of a computer or some devices, so we can have a flexible assembly without using PCB actually. You just need to have some sort of box to be able to provide wireless power through wireless power bus, whether it's depending on what frequency you choose, okay? And then you can place the chip freely with a lot of freedom inside the box, okay? And in this case, basically just have a wireless power supply and plus wireless data bus, and you don't have a lot of constraint to do your product design. So this could potentially revolutionize the future system design, product manufacturing. So this is not happening yet. I certainly hope that because I'm no longer doing the research myself, so somebody, you might be able to realize this in the future to revolutionize what we're gonna see electronic devices in the future. So please use your imagination. With that, thank you very much.
Thank you, Jianshan, for this very, very good, interesting presentation. I think that, this talk covers one of the, very interesting areas, which is wireless power transfer, that certainly we have many, many more interesting applications. Now, underlying those like application wireless charging, I think that, there's a fundamental microwave knowledge, you can learn from a course, you typically called microengineering, could be a different name in many other, many universities. I will strongly encourage students, if you are interested in learning and, pursuing the microengineering, you would like to take a course, before you graduate. Okay, so now let's move to our last but not the least speaker. Let me do Anding. Could you please share your screen while I'm actually reading your bio? So Professor Anding Zhu received the PhD degree in electronic engineering from University College Dublin, UCD, Ireland, where he is currently a professor. His research interests include high-frequency nonlinear system modeling and device characterization techniques, high-efficiency power amplifier design, wireless transmitter architectures, and a nonlinear system identification algorithm. For example, his research can be easily applied to wireless power transfer. So you can see that a lot of stuff are intercorrelated. Andy.
you, Shun, for the introduction. Yeah, I'm going to talk a little bit about 5G as Professor Franklin mentioned earlier, and also talk about a bit, how we're going to protect our environment. So, sorry. First of all, yeah, everybody knows this climate change, right? So this actually picture here, I was in Iceland in April. I can clearly see the glaciers melting very fast. So it's now just because the global warming and sea level is rising, right? So this actually became alarming, now the situation. So if you look at this diagram here, shows maybe a little bit difficult to see this. There's a number here. Each industry actually contribute to the carbon footprint. There's a say there's the transport could be 10% of those, and industry could be 20%, and so on. So each of those sectors actually contribution to the carbon footprint. They get a CO2 emission to the atmosphere. So then the people, or certainly we need everybody has to do something with this. So we have to encourage you to cycle to the university, to school, and to your workplaces instead of driving. And you can use eat less meat and eat less dairy food, and also recycle. Obviously, you need to recycle all those things. And everybody has to contribute to those to protect our the environment. But then what's the 5G to do? The 5G and actually basically is the 5th generation communication network. So those communication network mainly, there's the different from previous generation is much faster. So they can provide 100 times faster speed, right? So then also most important, they got 1,000 times of the large capacity, in comparison to previous generation. So what fundamental difference here, if you look at the previous generation communication, mainly try to connect people. So people has mobile phone, then people talking to each other. So there's many human, the connections. But now the moving to 5G, very different is that they try to connect everything, connect, the devices, machines, all those things together. So this is that you can have the, smart meters and thermostat, you have the refrigerator, and cars, and even your car keys, and everything going to be connected. So this is called, sometimes they call it the Internet of Things. They put everything together. So this is the difference from previous generation. So usually they use in triangle here to show what the 5G doing. The first of all, as I mentioned, the higher speed. So you can see your mobile phone connections, the Wi-Fi connection much faster than before. So this facilitated many new applications or even existing application much better. So if you play online games, you certainly need a very high speed connection. So make your quick response to compete with others. And there's also enable many other applications. For example, you have the remote medical operations and so on. So also another big triangle on the left side here, you see there's a massive IoT, which is IoT instead of what's Internet of Things, which is all the devices. So you can use those 5G network, connect those devices together, and then those can build smart cities. You can control your street lights, you can control the traffic, manage kind of traffic, and the element in the system. And another thing, there's a mission critical services. For example, you have the self-driving vehicles. They have to respond to the objectives very quick, right? So otherwise you got an accident. So those things are connect by 5G. And the 5G, we talk about CO2 emission. 5G certainly can help. Once they all network connected, certainly can help to reduce those CO2 emissions. And that's main thing. You just say, okay, you can everything connected, and then you can enable the automation, right? So you can make the machine to do this instead of manually to do things. And also you can optimize the system so that you can reduce energy and consumption. And in the end, you can reduce the CO2 emission. So those already happening in many places. So you can see the simple connection. If you connect the vehicle together to better manage your traffic, you can easily to get in 20% deduction on the CO2 emissions. Then the smart manufacturer, they can use in the 5G connections. They make the system much more efficient, so they can reduce the energy consumption. Again, they can reduce the CO2 emission. So there's a lot of things going on there. Actually, certainly help on those, but 5G itself actually has a problem. So what's the problem is that, for example, if you do, there's a lot of news already last few years. You can see there's a news talk about alarming, say the 5G itself also contributes huge CO2 emissions to the, to get those into our environmental issues. So there's many places actually even supply power, build a power plant for the provide power to the 5G network itself as the issue. So why there's the issue there? Where's the issue? So with basically, first of all, you already see, we see the number of the connected devices increase significantly. So those numbers, not just in the past, you only had mobile phone connection, right, between mobile phones. Now you connect everything into the network, and the numbers of the devices getting billions increase, right? So there's a huge increase. And secondly, you can see the amount of the data transmission also grow, and not just the number of connections. Each even you can use a much faster speed, and then you have the more data need to be transmitted. Now, as we know, every single bits you transmit and you always consume energy, right? So you moving bits between the devices, and certainly they consume power. You need power to transmit, right? So these cause significant issues to say, okay, this whole information technology side already made up 20% of the electricity consumption. So this is very different from previous years. So that's going to be continue to increase, right? So this is getting problems. This is going to be huge and greenhouse problems just for you're building this network itself or operating this network itself. So that's going to be a huge problem. Now the question is how we're going to do this result. Obviously, there's many levels to go. You can do better network management, better planning, and you build the higher efficiency network and so on. But now today we talk about the microwave RF engineers. So the answer to the question is, what can we do about it? So how can we help those things to make the system better? So I just give you some examples, say just for my own research and my own experience point of view. So if you look at the 5G network, or most of the wireless, we talk about wireless network part. So wireless, how the wireless is built up? Wireless basically they have the base station, right? So you have the tower. Then there's a tower going to be connected to the internet, but each of the tower going to cover a certain range of area, and usually from a couple hundred meters to kilometer range. So your mobile phone going to be connected to the tower, right? So then the tower connected to another part of the network. So then, because of the 5G now, actually each of these 5G networks is going to be much larger capacity because each of the tower going to cover a certain range, right? So if you getting more user into those, then you need more towers. So you're going to be build more smaller, shorter distance tower. But this tower, each of the base station and consume about 50% of the cellular network. There's a huge power consumed by the tower. So the base station there. Then under the base station, actually the base station part certainly include and the baseband stuff is the network part, and also their signal processing, that other piece. But of these 57%, actually 50% of those, you see this chart here, the 50% of those called the radio access part, basically the radio part directly related to what we're doing, RF engineer or microwave engineer doing the radio part actually consume half of those. So this was the problem with this so efficiency improvement in RF part in those 50% part certainly crucial, is critical. So if you can increase more, make this part RF radio part more efficient, certainly you can save energy. So then we dig into this. What's the radio part to do? Radio part basically you might learn this already in your courses. So basically a transceiver like this, right? So you have the baseband signal, the low frequency signal, your voice, your audio, your radio, the video and voice and so on. They code it in digital, and then the digital to analog conversion, they but the mixer, they're moving the frequency from low frequency to our frequency, and then transmit out. But before they transmit out, there's one element called the power amplifier. This power amplifier actually very simple functionality. They just amplify your signal because your signal relatively low and weak. Then we need to amplify that it to higher amplitude before they transmit the antenna. Otherwise, they're going to be attenuated through the air as it cannot reach your destination. So you need to get enough power pump out from antenna. So the power amplifier basically doing that. So they take the DC and power, as Professor Lin showed the diagram earlier on, to take your DC power from your power supply and then convert it to RF signal. So there's a conversion to there. And this problem is the main issue there here. It sounds very simple, mechanism, right? Just take the power, convert to this, but the efficiency very, very low. So that's the problem with this. How are you going to be getting this, the power pump out from your DC directly to air as much as possible. So if you look at the percentage of those, first of all, this power amplifier itself actually consuming, back to this diagram here, the rest of element actually relatively lower frequency, lower power. But this power amplifier itself consumes most of the power and in terms of the transceiver. So this over 50% of the power is the chart here. 50% of the power just consumed by this element itself. And then this efficiency itself actually very low. So it's about 20% lower than 20% of what it means efficiency, which means you put in the 100 watts in from your DC, draw 100 watts from your DC power supply. Actually, only 20% really converge to RF radiate out. But the rest, sorry, just go with something wrong with my slide. So the 80% power actually stay here, is not radiated out. And then this power actually became heat, right? It generates heat on the tower, then you can get in the heat there. So 80% power wasted and generate heat. Then this heat has to get rid of it. So we need actually cooler. We need to get in the cooling system to get rid of the heat. And not just the waste of energy, but also this cause other issues, reliability issues, others, because you heat up those systems, those PA going to be and less, a lifetime going to reduce. So there's a huge challenge. How are we going to get in higher efficiency for the power amplifier, pump more power to the radio side? But the fundamental problem is that the PA working like this, it has a lower power level, say the x-axis, there's a power level. The efficiency, when you're getting higher efficiency, high efficiency only can be worked out in the higher power level. If you drive the amplifier to the saturation level, and then they getting higher efficiency, your power coming out more, right? But the problem is if you drive it harder, then PA actually the gain drop, so which is cause linearity issue. So there's not a linear amplifier anymore. So that's the cause issue you have. If you want, you don't have to have both these things. You have to get in, if you want higher efficiency and you destroy your linearity. Certainly linearity is a problem. You don't want to amplify the signal, distort the signal. Otherwise, your receiver side cannot get in correct information. So your customer wouldn't be happy, right? So this contradict each other. The efficiency, linearity, always the issue. So how are we going to solve those? Actually, people try to many ways, right? So they try to get in better device, getting higher efficiency devices and getting better design analog domain, and try to get in better design methodology. There's people work on that, and many people work on the better PAs and better, the architecture, and better even the whole process and so on. But one of the example what I was doing have been doing for 20 years. The idea called digital pre-distortion. So those was the concept I tried to do. So basically, it's a very, very simple concept. So you say, okay, we are showed the PA is a nonlinear device. So the problem with if you drive the PA to higher efficiency region, you cause a linearity issue. Now, this thing cannot be solved within the PA itself because this always contradict. So what do? We can jump out of the box. And digital distortion basically doing, say, okay, why we say the nonlinearity problem? The nonlinear problem basically affect my signal. when the signal come into input to the PA, output is going to be problem, right? So then the idea is that, so why we take the linearity issue out, so we build another box before the signal get into the PA. So we can build the, like if I look at the PA behavior like this, so the input output relationship, there's a lower amplitude, the linear amplification. Then when the power goes up, then gain drop, right? So could bind this way. And then if we build another box, in this box, basically transfer function going to be inverse order. So the lower power, they're going to be the bandit, then go to linear this way. So they're going to say, well, if this two box, cascaded box, the behavior into mathematical point of view, if these two function inverse each other. So I put in the signal before it's first I'm purposely bind this way. Sorry, go back here. Then when the signal pass through the first box, then come into second box, then the signal going to be coming back, right? So it's from the original input to final output, you got the linear, right? So there's a linear amplification. Then in this case, you say you still can drive the PA to very nonlinear, and then this can have higher efficiency, right? But the DPD part, the digital distortion part, can process linearity issues. So and this one can move into baseband to move into in the transceiver architecture I showed earlier on. You can process this one in the digital baseband. So then you can get in nonlinearity back to the final signal going to be linear. So this conclusion that you can get in high efficiency nonlinear PA, and also these getting good quality signal quality, right? So obviously they doing this, you do simple math there. Say even this one, if you include the digital distortion box there, obviously you need extra circuits, right, to implement those. And in order to do this, also you need to build. Sorry, it's always automatically play to next one. Anyway, so you need to take some signal out from in order to know how to build the nonlinear function. You need to build exactly inverse of those. You need to know what the behavior of the PA, right? So you take a partial signal coming out from the PA, compare with original input, then you build the model for those, and then this model together, if you model is accurate, so they can do this and linearize this system, right? So if you do simple math, say usually the PA in the base station, they could be a couple of 100 watts, right? And then the digital circuit, as we know, digital circuit usually quite power efficient, quite low power, so they can run in very low power. So if you look at here, if I 200 watts in the base in the PA, I got a 10% back, I can get a 20 watts, but the extra circuit here only consume a couple of 100 milliwatts. So certainly you can save a lot of energy on those. So there's the technology. Basically, you can see they can boost the system over 30% in most of cases. So then you can see this is actually significant change in the environment and economically. So if you consider today, roughly about 7 million base stations deployed in the 4G, just the 4G network, and not talk about 5G yet. So the 4G network, each of the base station could be consumed as 10 kilowatts power. So you do simple math here. This is 10 kilowatts, 7 million. That's going, the 70 billion watts, right, in total, right? So if you talk about 30% of those, actually you get to 21 billion watts. So this is actually a huge difference. So that's what usually I talk to my students, they're proud of those. This idea, simple idea, building the base station, and most of the base station, actually every single 4G base station now has those digital distortion chip built in. So that's what the RF people can do this work and make a difference, right? So if you're thinking about changing the world, changing, protect the environment, actually this is one of these simple things you can do. Obviously, this is not easy, right? So it sounds very simple. You can just build the nonlinear function, then put it there, but you have to make sure that exactly inverse each other. So that's you need a signal processing algorithms to do that, not just RF circuit design. It's RF circuit. You need to understand how the RF circuits works, and also you need to know the signal processing. As Professor Gong mentioned earlier on, say the machine learning neural network, people talk about those, right? Actually, we use just 2 days ago, we published one paper and on IEEE transactions actually using neural network, using machine learning algorithm to build this function for linearize these, the PAs, because the PA behavior getting much more complex today. So that's just one of the examples, show you how we can do this. And the second thing, show you the example here, this transceiver system part also innovation. So there's a lot of innovation going on here. Now in the previous generation, usually you got the transmitter, you got a single antenna. This is single antenna going to be omnidirection transmit signal. Doesn't matter where your device is located. So and the tower does it just transmit a signal. But this actually waste energy. So what happened is now in 5G, they changed this, change called directional operation. And that's what the Professor Lin mentioned earlier on. This is called the MIMO system, which is for the multiple antenna together. You build multiple transmitter chain. And there's a simple actual operation. The principle is that there's electromagnetic wave radiated to the air. If you generate a signal and there's a wave, actually just to control the phase, the different phase as a different location, then you align them. Some of the wave going to be add on together. Some of the wave at a certain location, they cancel each other. Then you can form this kind of called beam to directly be pointed to the user. Where is the user located? Only the signal coming to when the user located that place, you transmit it to that direction. Other place you don't transmit energy. So that's say here, just example here showing energy efficiency improvement. You can see the single antenna, if you omnidirection, this is energy or wasted in other places, not close to the devices. But if you get in the multiple antenna together, you can easily get in these huge deduction of the energy. So that's what the 5G going to do, more kind of directional the transmission, so that you can use those technology to the transmission of your signal from the transmitter to receiver. And also as Professor Lin mentioned, that you can use this one maybe for power transport too. You can more efficient to do the power transfer from one to another. So just to give you some flavor on those, that's just 2 examples on doing this. So conclusion here is just to say, okay, 5G network certainly connect more items to the network. That's enhance the way we're doing things, right? So, and also the could we revolutionize many systems from smart city, intelligent transport, and so on. But and also 5G can have the CO2 emission, but make this 5G green. Actually, our microengineer actually play very critical role in here. You can do a lot of things to improve the network to protect our planet. Thank you very much for your attention.
Thank you, Andy. I think it's also another very good presentation. I think that we see another aspect of microengineering, active circuit, particularly, and also how it's used for all the applications and also its social impact. So, all right. So this is the end of all 3 presentations, and so now it is the Q&A time. So you can have 2 ways to submit your question. You can either type in the chat box, or you actually prefer to speak. You can use the raise hand function. So all you need to do is just move the mouse to in the participants list, move the mouse to your name, and there's a hand. Okay, so you raise your hand, and I will see you, hand raised, and I will get to the questions, one by one. Okay, so because if everybody is speaking, then we're gonna into a classic so-called like a party talk, issue. All right. So actually, I saw Professor Kerr, whose hand is raised. You would like to say something?
Oh, no. Actually, I made a mistake. I think let's hopefully more students will ask questions. Yeah.
Okay, thank you so much. Yeah, and also, by the way, Professor Carroll is very well known for his research on substrate integrated waveguide, which was mentioned in Dr. Franklin's slides. Okay, just for your quick information. All right, so let me see. Any student who's online and or you are in a classroom, you can actually ask the question you can start to think of the question. But actually, there's a question already in the chat. So let me, I think Dr. Jen Shenling briefly talk about that. So a student asked, I don't know, he is, I mean, it's a Samad Atta. So the question is that, do you think it will be ever possible for larger structures like homes to be wireless powered? Honestly speaking, this is something what I want to do. I hate wires, you know, I don't want to see all kind of wires in my home. So Dr. Ling did show a kind of like a conceptual picture about this thing is happening. I think there's probably was demonstrated to some extent publishing a Nature journal, right? So Dr. Ling, you want to like to make up some, you know, maybe more detailed comments about the feasibility of like, so, you know, can we really power everything or maybe part of the things in our house? You know, at least we can cut, you know, say a lot of wires, right? So that would be nice.
Well, thank you for the opportunity. So I wouldn't rule out any possibility unless it's physically impossible. So I would say that it's potentially possible. It just really depends on engineering effort, research effort to come up with better technologies. And certainly you all need to meet the safety requirement. And probably right now, not everything can be wireless powered. It really depends on your power level. And it really depends on how the two curve. One is the power requirement going to drop over time. Yeah, one is the technology possibility going to increase over time. Eventually, it's going to be an intersection there. And then in terms of, I saw that someone was asking about wireless power grid, the concept. Actually, some companies are actually looking into that, working on this kind of stuff. And definitely, I would like to have that too, at least for emergency backup. When a hurricane hit, you probably notice how many homes in Florida lost power for so long, so many days, weeks. And wireless power grid could potentially solve the issue.
Thank you. Another question is related to education. So Muhammad Al-Habi asked a question is that what is the recommended certificates for fresh telecommunications engineer graduates? So, well, I guess, you know, every university does it differently. So now, fortunately, we have professors from different universities. So I would ask one of the speakers who would like to address this question first.
Can you clarify what they mean by certifications?
I'm not quite sure. Or Mohammed, are you online? You can unmute yourself. Maybe you can clarify your question a little bit more.
Yes, hi. So thank you for the presentations, Prof. And my question is related to, like, in the field of the telecommunications industry, like, what is the recommended certificate for like fresh graduate engineer? So I'm not sure if it's still unclear.
Yeah. So I think you're asking sort of like, do you have to become a professional engineer? Do you need a professional engineering certification like you would in like in civil engineering? You know, you can't get a job without certification. Ours is more around training. So I would say your best opportunity to get to your best chances of getting the opportunities is having coursework that allows you to demonstrate to an employer that you have the skill set to work on the kind of problems that their organization does. At least that's the way it is in, as far as I know, in the US. A lot of that is really contingent upon, you know, do you have the training? And so if you're an undergrad, some campuses will have technical electives that students can take in general, and then they have graduate courses that some students can take as well if they've demonstrated reasonable proficiency in their prerequisite courses to that. But I think right now, to my knowledge, there's not a certification requirement to do RF as much as there, at least for traditional RF. Now, you know, Jen Shen, I'm thinking about power transfer. I can imagine, because that's that connects more to the utilities. I can imagine that might eventually have some requirements just because it touches everybody and it could be a safety issue. But in terms of regular communications, as far as I know, that's not an issue. And I think for high power applications, that's a really niche community. So I'm sure they have some training that they require employees to do before they can implement and work on anything that's considered high power, which is, for me, high power starts in the thousands of watts, other than your microwave oven.
I can add some points. Is that certainly some people will pursue a graduate degree. If, for example, master degree focused on microengineering. But I know that maybe not everybody is that fits in everybody's time schedule. Some universities are thinking about provide some certificate program, which is not a master degree, but it will require you to take a few courses. Not as many, not even close to as many as a master student needs to take, but which allows you to take a number of courses in a focused area, so that you actually gain more experience and credentials. So actually, our University of Central Florida, is considering to create a certificate program at the graduate level. But people can, mainly from industry, they're working and they can take the course and get the certificate, which allows them to become more capable in the microengineering. All right, so let's move on to I think an audience. His name, it's his or her, Angelo Ferraro. So you raise your hand, and now it's your turn to ask a question. So feel free to unmute yourself and ask the questions.
Thank you so much, Professor. Yeah, my name is Angelo Ferraro. I'm at the University of South Carolina, and this is not so much a question but comment, but I wanted to thank all of you for presenting such a wonderful workshop on RF. It was sorely needed, and so you filled the need that was there. My comment more goes to almost anyone in the audience. If they wanted to continue developing this interest and the skill set in RF, one of the things that they can do locally through the IEEE is create, if they don't already have a chapter or a student branch for RF for the different societies, they can start one. And I happen to be in South Carolina, also the chairman of the Columbia section, which is about a third of the state. And if anyone in my area would want to start a student chapter or an industry branch, or actually opposite, a student branch or an industry chapter as part of one of the IEEE societies, I would love to help them here locally. But every single one of the different regions that this webinar is being transmitted to, they also have their local sections that they can get assistance from to try to get a chapter or a branch started, and to help continue with their career development and other interests of just getting RF out there, and also help with things like licensing, because depending on which jurisdiction and the frequency bands, there are different laws that restrict transmission of certain power levels in different bands of frequencies. And so they can also help in that aspect. So I just wanted to make that announcement. My guess is anyone in any of the other regions could also do the same thing. But thank you also for such an excellent workshop.
Thank you for your very good comment. And actually, I'm the I have another hat. Where another hat is, I'm the the MTT Society Regional Chapter Coordinator for Region 3, which actually South Carolina is in Region 3. So if you are interested in forming a student chapter or industrial chapter, feel free to contact me. I will work with you to on that. Okay.
We've already started other societies and chapters, but we don't have one for RF, and I was hoping that some of the students from South Carolina would be interested in doing that, and obviously to contact you and myself to help that started.
Absolutely.
Thank you.
Absolutely. Okay. So, all right, so let me look at the question here. There's a question from Michael Brown, and that is a question for Dr. Lin. So from my understanding of wireless charging, one major challenge is to provide power to a system without impacting or interfering with the performance of nearby system, as well as the system's internal components. Is the advancement of wireless charging limited by interference with existing technologies or by hesitancy of new system to design for its implementation? So, Dr. Lin, could you elaborate on this thing?
Sure, thank you for the question. I just typed the answer into the chat,
Okay.
but be happy to elaborate a bit more on this. So certainly the interference is always the issue, not just for wireless power, but also for all existing wireless systems. There were so many wireless systems operating right now with so-called active system, active transmitting signal, or passive system, which is actually not transmitting but receiving system. So all the wireless system need to meet a certain the RF transmission regulation rules. And because wireless power technology is relatively new, so certainly the government agencies, especially the regulation agencies like FCC and TIA, they are certainly closely watching the development. And the rule is not always stay there forever. There's potentially going to be change, and certainly you notice that we have so many wireless systems right now competing the spectrum. How do we make sure that they all coexist together harmoniously without causing issue? So that's a constant the research development and certainly the challenges that many people are working on. Hope that answers your question.
Thank you. Any other question? Let me see. I saw question. Actually, I think a question from Jose, but it was answered by Rhonda in the chat. So I would like to give opportunity to the students, if possible. Any if any, I don't know. Let me see. Oh, there's a question from Sailing Bomali. The question is for Andy. So, to what degree digital pre-distortion solve the nonlinearity problem of PAs? Can we see a decent linearized behavior at the output with this technique? What are the limitations of this technique? Very good question.
Yes, great question. So the linearity actually improves significantly, and if you, as I mentioned earlier, and now almost every single 4G base stations using the DPD technique. 5G certainly they're going to be continue use. So they put on this, the linearity can, they can increase, improved by 20 dB, even 30 dB. So before the signal, without DPD, actually the system does not work at all. So linearity is very, very bad. So that's what obviously depends the system requirement. Sometimes the system more stringent, sometimes it's less. So you can design, again, this algorithm pretty flexible. You can get in higher performance with more complex models, right? So you can design more accurate models. And sometimes obviously more complex, more accurate model, you need a bit more complexity. So it's really trade-off between in the real system operations. So there's a lot of flexibility. Limitation now, I think the move in the 5G, the limitation there, because the power PA actually power drop, not like in 4G, because they cover longer distance. The power amplifier usually running a couple of 100 watts. But now, as I showed earlier on the 5G, because the cell became smaller, the distance shorter. So that's which is your output power from the PA actually lower. It's a couple of watts. Then you're still doing digital pre-distortion in your baseband. You still consume a couple, 100 milliwatts. Then ratio became smaller, right? So your gain relatively smaller. So that's why in 5G you have to design more smarter or more, the better model to model these nonlinearity. So getting reduced power still consume, they consume less power, but they got in better performance. So that's why the research still going on there. That's why we need a better, more smarter algorithm to do that. I hope that answers your question.
Thank you. think that's a very good answer. Any other questions?
I have one.
Yeah, go ahead.
I mean, given the field of microwave engineering or RF, it's more about circuits. I mean, the first picture that we get when we speak of microwave or RF, it's like we get a picture of circuits, we get pictures of passive circuits or active circuits. But as I observe in the presentation of Dr. Zhu, instances were mentioned about machine learning and I mean neural networks. I mean, as microwave engineers, are we separate from the machine learning people, or are we including the skills of a machine learning engineer inside the microwave community? What's your take on this, sir?
Yeah, from my own experience, certainly you see here, I showed my example there doing digital distortion. Certainly you need a significant knowledge on signal processing. It's not just RF circuit cell. So it's across two domains. And so that's why the microwave engineer, not like previous, I would say the many years ago, you only doing circuit, as you said, you any RF circuit, RF people only doing circuits and doing the analog part. But actually now the system became more integrated. Multiple part. Not just one field you can do the job. So you need to understand the system, the whole system. That's why the signal processing actually play significant role in those RF circuit design. It's not just for digital distortion. It's one of the example. But others, for example, now you design analog circuits itself. You need optimization algorithms, right? So some colleague work on the power design or other designs, you need optimization algorithms. Those optimization algorithms and also the signal processing involved, right? There's algorithm involved, the mathematics behind those, not just so you tune in circuit, not like you try an arrow. So there's a systematic algorithm you need to understand. And further on the system now, you need to understand the signal processing part of signal also. It's not just in the old days, you test the RF signal, you only use a single time, two-time signal. But now you use a modulated signal, which is directly communication signal. So you need to understand what the signal you're going to transmit, you're going to receive. So there's also a lot of knowledge there you need to understand. The machine learning certainly can have significant help actually circuit design, analog circuit design, and optimize the circuits and do a lot of linearization. Certainly needs those algorithms. So they were not separate from those. There's, of course, we mainly were using those algorithms, apply those algorithms in this domain. So that's increasingly important. Actually, the next year, IMS 2023, we're going to have a called AI ML Day for the International Microwave Symposium. So there's going to be a lot of activity going on to gather those papers in this domain. I think would that answer your question?
Yes, thank you, sir.
Thank you, Andy. Thank you. I think you got more questions coming in. So there's a question which is quite technical, in my opinion. Probably more technical than the average, level for this type of a webinar. But I think it's good. It's like for you, is a short question on digital pre-distortion. Can the digital pre-distortion work with the envelope tracking PA supply, which needs the precise envelope information? Try to keep it at the layman language because
I think it works. I would say this digital distortion already used for envelope tracking PAs, and actually there's many years ago we already developed the Qualcomm has a chip doing this, so there's already built into your system. So there's now currently most of the digital distortion work for base station, right? But now actually moving to handset too. So moving to Wi-Fi to many different places. So digital pre-distortion only one of the algorithms. They can uniformly use it for many places. Actually, for example, there's the satellite communication. I work with the European Space Agency. They try to put the digital pre-distortion on the satellite because they improve the efficiency of the satellite communication, right? So there's many potential to do that. So they're going to be, because algorithms, right? So you just characterize the nonlinearity. Anywhere the nonlinearity need to be compensated. So if you find the accurately model this non-energy, you find algorithms to inverse those. That's always the potential work there. And that, I saw another question say the digital distortion used for class C. I mean, I say answer is yes, but usually we don't, the class C maybe combined with other architecture together. For example, you're doing Doherty amplifiers, and there's non-energy there. You need to compensate those, not just a single amplifier model itself. So that's quite the universal kind of algorithms we can do.
Thank you, Andy. I think we are, running toward the end of this webinar. I think it was a very great webinar, and I know that a lot of students are here. And in addition to, the your interest in the microengineering and potentially take a microengineering class, I would strongly encourage you to join MTT Society as a student member. And by the way, the cost of if you are already IEEE student member, and it will cost you another $1. Is that $1 or 50 cents, Ending? I think it's either 50 cents or $1 to become an MTT.
Yeah, I think $1 for full year. I think the 50 cents maybe for half year, something like
that. Yeah. So it's $1 extra for you to become not only IEEE student member, but a MTT student member as well. So this actually, I think the cost is minimum, but it will allow you to access many resources. For example, if you are MTT Society student member, you can watch all the videos, the past webinars under the MTT Society Resource Center for free. Okay, if you're not an MTT Society member, actually there's a reduced fee for you. So there's a lot of advantage. I would strongly encourage you to pay $1 extra to join in, and be participating in various IEEE activities. And we expect to have this DMI workshop next year for this same region, but we do 3 workshops around the world. But for example, this is a good time for the North and South America. So let's thank the 3 speakers again. And again, all this webinar is recorded, and you will be able to see the video very soon. And also, I would like to have a copy of the slides from each presenter. If it's okay with you, just email your slides to me. So if any of the audience would like to have a copy of the slides, just contact me, and my email is in the chat, so you can actually send to me. All right. Okay, thank you everybody, particularly for ending. It's a you are at Friday evening, and which is usually family time, and I really appreciate everyone putting time and excite our young students, to get them excited. And I can guarantee that this is an exciting field, and I have been enjoying, doing research and studying in this field. And I'm sure that all the speakers have the same feeling, and many of them. MTT Society is one of the largest societies within IEEE. I'm not sure it's the top number 3, the 3rd largest or not, but used to be 3rd largest. But I think we have on average around 10,000 MTT Society members. So it's a big family, okay? And we have a lot of good. Have a good weekend, everyone. Bye.
Sean? Can people see the videos without being a member, or do they need to be a member to see the videos?
Oh, for this particular DMI workshop, we make it for free for everyone, with or without even IEEE member, because this is not something we make money for. Yeah, it's a free for everyone. Yes.
Okay, excellent. Yeah. Thank you so much. It was really nice seeing you guys again, and I enjoyed your talks.
Bye.
Yeah, nice see you. Nice talk. Okay.
Thank you. Bye-bye.
Bye-bye.
Bye. Bye-bye.